Welcome back. We have just started to talk about spontaneous instability and dewetting in an ultra thin film. Now, this word ultra thin film should be clear to you. In our context, ultra thin film is a film, forget about numbers, where we are defining that there is active van der Waals interaction between its two interfaces. So, this is the most important term, active van der Waals interaction. It turns out that between two surfaces, van der Waals interaction stretches roughly about 100 nanometer. Arguably, some people say it's even lesser. Doesn't matter. So that's why we will stick. What is a thin film or an ultra thin film? Where there is active van der Waals interaction between its two interfaces. And of course, what are the necessary conditions for the film to become unstable? So one of the things we need to understand is very clearly is the spreading coefficient. The sign of the spreading coefficient plays an important role, because please do not forget the native oxide layer on a pure silicon surface is just 1.5 nanometer, 1.5 to 1.8 nanometer, and it is most difficult to dislodge. It would have been very good from the standpoint of microelectronic fabrication had this layer been unstable, it would have ruptured on its own. Doesn't happen. So the moment a film is very, very thin, it may not be unstable. It is unstable only under certain conditions, and one of the first criteria for an instability is the sign of the spreading coefficient. Of course, what the spreading coefficient does not take in account is the thickness of the film. So even if you have a very thick layer, where based on the local surface energies, if the spreading coefficient, even if it is negative, spreading coefficient, that layer is not going to rupture, or no instability is going to be manifested, because a thick layer is sort of stabilized by gravity, and therefore spreading coefficient, despite having a negative sign, will not influence the film instability. In fact, the situation becomes more complex, and the so called spontaneous instability is manifested only when the film thickness is very, very thin, thinner than this limit up to which the van der Waals interaction, the effect of van der Waals interaction stretches. Why? In order to understand that, we now talked about another additional concept, and that is the dynamic steady state prevailing on the surface, on any free liquid surface. And what is responsible for this dynamic steady state? The kinetic energy, internal kinetic energy of the molecules are responsible. They sort of lead to some fluctuations, but that does not cause any damage to the liquid surface, right? Because these fluctuations are high frequency, very low in amplitude compared to the macro scale. So if you have a 10 centimeter deep water in a beaker, or 1 meter deep water in a bucket, or few hundreds of meter depth in a reservoir or a pond, or maybe few kilometer depth in an ocean, it hardly matters, because this amplitude is few nanometer. But so what happens, because of the internal kinetic energy of the molecules, the surface fluctuates, and the moment there is fluctuation, it enhances the surface area, as we have seen like this. So that sort of triggers the Laplace pressure, which flattens out the film. So surface tension driven Laplace pressure flattens the film or stabilizes the film, and there is in fact no destabilizing field at all. The problem becomes more complex when the film thickness is below this range, or in other words, the amplitude of the oscillations becomes of the same order of that of film thickness. And then if one looks or examines a snapshot of an oscillation at a specific time scale, then certain important things needs to be looked into, that at any given instance of time, the film is not flat, but there are in fact fluctuations, and because of this fluctuation, the strength of the van der Waals force at point 2 is stronger than that at point 1, and therefore this is a deformable interface, not therefore, this is a deformable interface, please understand that. And this is experiencing a force exerted by the presence of the substrate, which favors the growth of the amplitude. So now you have for the first time a factor that in fact can favor the growth of the amplitude. So Laplace pressure is still present, Laplace pressure is still trying to stabilize or hinder the growth of the amplitude, but the so called van der Waals force driven disjoining pressure is in fact trying to enhance the amplitude instead of letting it to flatten out. So, there might be a situation in case the strength of the Laplace pressure, van der Waals force driven disjoining pressure is stronger than the restoring strength of surface tension, then the amplitudes, the fluctuations, instead of stabilizing down with time, might in fact grow, and grow up to what extent? Well, they will in fact grow. So, typically we are used to this, you have a fluctuation and you know who is responsible for this flattening, it is the Laplace pressure. But in a thin film, if you have a fluctuation, there is now a competition between Laplace pressure versus van der Waals force driven disjoining pressure, and as a consequence what happens is, in case the strength of this disjoining pressure is stronger than the Laplace pressure, then the amplitude will grow, but grow up to where? It will grow till the bottom of this fluctuation touches the substrate, or the amplitude matches the film thickness. What would that mean? That would in fact mean that the two interfaces, the liquid, the free surface of the liquid and the liquid solid interface, these two in fact have merged. Merged to form what? These two have merged to form a three-phase contact line, and that is associated. So, it is like this now, that is associated with the formation of a hole. So, this is it. So, with progress in time, the amplitude in fact grows, right, and therefore, that is associated with the formation of a hole. So, what has in fact happened? Your film has ruptured. The formation of hole in fact is an indicator that the film has ruptured, right. This is how it goes. So, formation of the hole in fact is associated with the rupture of the film. In fact, we are very close to I am very close to showing you a real video which will tell you what exactly happens, but before that I must highlight one very fascinating aspect, and that is, from the discussion so far you have had a feeling that the destabilizing effect is due to due to van der Waals force or disjoining pressure, and the stabilizing effect is by surface tension. But an amazing thing happens the moment the film ruptures. So, this is a hole, and you see it has formed a three-phase contact line. In fact, the rupture takes place like this, it does not take place like this. there I will talk about the fact that these amplitudes have a lambda, the periodicity of the amplitude I will not take up a full mathematical treatment, but the periodicity of this oscillation amplitude lambda is much greater than film thickness. In fact, this form of instability is the reason it is called long wave instability. So, what does it mean? That the contact line forms like this at a very low value of theta when the hole forms. Now, does it remind you of anything? Well, now you have a different situation, and what is the situation? You have a solid substrate and you have a layer of ruptured liquid. Now, is it clear why this so called liquid thing is important? Because of the fact that in case you do not have a liquid film, right, if you have a solid film which is rigid, you might have these type of van der Waals interaction, active van der Waals interaction, but the interface, this interface is no longer deformable. So, it is too stiff and therefore, it will not deform. Therefore, what happens is that even if you are doing experiments with polymer, at room temperature the films do not dewett. For a polymer whose Tg is at an elevated temperature, let us say 100 degree centigrade or something like that, at room temperature the film does not dewett. Now, you understand that in fact, at room temperature even this fluctuation spectrum is sort of significantly absent, because it is a stiff interface, it is a hard film. But when you take it to the liquid form, you start seeing all these things, right, and therefore, depending on the strength of the disjoining pressure, and if it is stronger than the stabilizing effect of Laplace pressure, it is possible that the instabilities or the undulations grow. Now, once the amplitude has matched that of the film thickness, you now understand that the film has ruptured. So, you have a liquid over a solid, but what do you additionally know? You additionally know that for a liquid and a solid system, it has a specific equilibrium contact angle that is given by, you all know that now, given by Young's equation. And look how it has ruptured. It has, in most cases, it has ruptured with a very low value of theta, as if it is like a tangent and it simply touches. So, since it is a long wave instability, rupture takes place like this, very low initial value. So, now what will happen? If you now try to balance the forces over here, this is the intrinsic contact angle, and you see that the horizontal component of forces are no longer balanced. In fact, this meniscus now wants to retract up to when? Up to the point when theta I matches theta equilibrium. So, you see a retraction of the contact line on the solid surface, which is dewetting, and it is associated with growth of the hole. Fair enough, hole grows. In fact, the reality is even more complicated. We will soon see that when we talk about little more about the experimental details, after we of course have a fair deal of idea about the disjoining pressure. That is my priority now. But what force field triggered this retraction? And before that, let me just highlight this. What do you know? Destabilizing effect is due to van der Waals forces, stabilizing effect is due to surface tension. But now look here, what force field is triggering the retraction and hole growth? Well, it is nothing but surface tension, right? Why? Because Young's equation is not valid in this configuration, and the retraction continues till the horizontal components get balanced. So, that is very interesting. In fact, what we just realized, that there is in fact a role reversal of surface tension before and after the rupture of the film. What does it mean? That till the film has not ruptured, the surface tension or Laplace pressure in fact tries to stabilize the film by suppressing the growth of the amplitude. But the moment the three-phase contact line has formed, the film has ruptured, in fact surface tension now aids hole growth. So, there is in fact a very fascinating role reversal of surface tension before and after the rupture of the film. Having said that, let us sort of look into some of the movies. I am a bit sorry, this movie is not working from here, I will just run it. So, here you can see what you are now seeing is in fact a polystyrene film. In fact, it is difficult to even get to the original configuration, its dynamics is so fast. What you are seeing is a polystyrene film, a spin coated 40 nanometer thick polystyrene film, simply heated beyond its glass transition temperature. You have not done nothing else. The film has been spin coated from its solvent in toluene, and then you simply heat it up beyond its glass transition temperature. You actually, this has been imaged under an optical microscope using a real time camera. See what happens. So, you already see the holes, which now you should understand that these are these holes. The film has ruptured, and you see the film is growing, the holes are growing, and there are some dark spots here, and these holes have grown so much that you suddenly see the film is completely disappeared. And in fact, I have a nice late stage image, late stage microscope. So, you see this is what happens. I will tell you what happens before I explain. So, what happens is here, for simplistic discussion, we have talked about the growth of a single hole, but reality is that there are multiple holes on a film. Actually, under experimental condition, multiple holes form, right, simultaneously due to the same physics. In fact, one of the things that you might have noted is, I am really sorry it is not working from the PowerPoint, that every hole is sort of, suppose if you are tracking this particular hole, it is sort of surrounded by a thicker outline. And it turns out, these are hardcore experimental facts, that every hole that appears has a circular rim around it. And so, its configuration is not like this, as we were talking just to explain the role reversal of surface tension, etc., etc. It is more complicated, and it turns out the rim formation is attributed to a mismatch in the rates at which the polymer or the material is dislodged from the surface, but it has to see, that is another advantage of using a polymer, it does not evaporate away, because if you use a highly volatile liquid, it will, holes will form, but the material will simply evaporate away, therefore, you have no idea where the material has gone. But here, since it is a polymer, it has very low vapor pressure, it does not evaporate away. So, this material that was there in the area, over the area where a hole has formed, has to get diffused to other intact areas of the film, and so there is a mismatch at the rate at which the liquid is dislodged from the surface and gets redistributed to other intact areas of the film by diffusion. There is a mismatch, and that manifests with the formation of rims. So, now these holes are growing, each one of them has rims, and so what happens with when the diameters of the individual holes become larger, the adjacent rims touch each other. So, with time, resulting in some sort of, the holes are now completely gone, the morphology changes totally in some sort of a cellular structure, as you saw in the second movie. You see some cellular structures like this form, and what you can conclude is you had a hole over each of these areas, which has sort of grown in size, their rims have joined up with each other, forming a cellular structure. Now, these cellular structures, in fact, you need to consider the mass balance. So, the entire material of the film that was spread over the entire surface is now confined in this narrow thread. So, they are sort of very tall and long, tall, sharp and sort of very long threads. So, they are very high aspect ratio threads, and these type of threads with liquid threads with time exhibit an instability that is known as Rayleigh instability. I am sorry, I will not have the time to go into the mathematical formulation of Rayleigh instability, but one can take the Young Laplace equation in an axisymmetric form, in a more generalized form, and one can very easily explain Rayleigh instability observed in a long liquid thread. But anyway, what happens is these cellular structures eventually break down due to Rayleigh instability into isolated droplets. You see, for example, if you look at, I'll repeat this movie again. So, if you look here carefully, any one of these threads, say you have a clear thread, and with time this thread is disintegrating into, see here the thread is about to break down, just follow that mouse on the screen, and it forms isolated droplets. So, that is how the morphology of a dewetted film looks like. There are two aspects. So, now I guess this image sequence makes sense to you. There are other critical issues. I mean, what you actually see here is some sort of a secondary instability around the rims. Let us avoid those complications for the time being. So, but what you observe is that you start off with a flat film, and what have you done? In fact, you have done nothing apart from heating it up, and based on its own own thermodynamic consideration, the film itself has evolved. So, the first the film has ruptured, then the ruptured holes have grown in size, and then eventually this has led to the formation of droplets. So, there are several issues one can argue whether. So, first thing is that the science is very, very fascinating. There have been people who have contributed significantly into these areas, but if you look into the whole evolution sequence, there is something very fascinating that comes out. We have been talking about so many complicated nanofabrication techniques, thereby you do soft lithography, you do this, that, but here you see that you have done nothing. You had taken a flat film which is so easy to create by spin coating, and the film has evolved to form these droplets, which are again few microns or even smaller than that in size. Only problem is that these are random. So, you need to think of doing something so that one orientation of research is to sort of align these structures, and you will be very fascinated to note that often these structures are aligned by dewetting a film on a soft lithographically patterned template. So, soft lithographic technique is a top down technique. This is sort of a self organization technique or a bottom up technique in some ways. So, you essentially combine the basic concepts of top down and bottom up approaches to create some very beautifully ordered structures. Research also has moved into, I do not think I will cover that again, that there are issues where people are looking at how to enhance the stability of thin films even on non-wettable surfaces, because that becomes very, very important, because of this type of possible rupture due to spontaneous instability, people avoid ultra thin films, and now you understand that films are very important as resist layers and things like that. And since the feature sizes have really come down in microelectronic devices, often it might be necessary to actually look into for very thin films which are stable. You do not want your photoresist layer to rupture during your photolithography process, right. So, these are the issues which people are looking at, but I will talk more about dewetting and how to align the dewetting structures, etc. But before that, in the next lecture I am going to take up the interaction between the van der Waals interaction between two surfaces, which will give us a mathematical foundation to understand disjoining pressure. Thank you.